On Monday, we started how the lift changes as the angle of attack changes, right? So basically, we use the result of thin airfoil theory and reached the conclusion that as you change the angle of attack, the pressure distribution is equal to the original pressure distribution plus a universal function that corresponds to a flat plate solution. And we can use that flat plate solution to figure out how does the angle of attack changes the lift, as well as how the center of lift shifts as we increase the angle of attack. And that relates to stability of the airplane, right? As a reminder, the stability of the airplane relates to how the center of lift shifts as you increase the angle of attack. What you want is the center of lift shifts in a way that restores the angle of attack change. So that means if the angle of attack increases, you want the center of lift to shift in what way? Lift points upward. You want to shift downstream, right? So that the angle of attack restores. If the angle of attack decreases, you want the center of lift to shift forward so that the angle of attack is going to be restored, right? Okay. So today, let me actually start to introduce a way that makes it easier to contemplate the stability of an airplane. So that has to do with the introduction of the aerodynamic center, the quarter chord. Right? So instead of thinking about the moment around the leading edge of the airfoil, as we did on the whiteboards on the walls on Monday, let's shift our attention to the quarter chord and think about how the moments change around the quarter chord. The reason we are thinking about the quarter chord is because if you increase the angle of attack, right, it's because actually the flat plate solution has zero moment around the quarter chord. Right? So remember, the moment around the particular location, let's say the moment around quarter chord, let me say, is equal to the integration from 0 to c of the pressure, actually the delta pressure, pressure lower surface minus pressure upper surface, right, times x times dx. The whole thing times the span, right? So that's actually how much moment is around a particular, actually around the leading edge. But if you want to compute the moment around the quarter chord, you need to change the x from x to x minus a quarter chord. So that's the formula for computing moment around the particular point, right? Now, if this P is the solution from thin airfoil theory on the flat plate, then we know that this is equal to 0 if the PL is equal to the P flat plate and the PU is equal to minus P flat plate. And that is the solution we get when that's the difference in the solution we get if we increase or decrease the angle of attack. Right? This is particularly nice because if we increase or decrease the angle of attack, then the moment around the quarter chord, the delta moment around the quarter chord, is going to be equal to the same thing, right? From 0 to c, the delta PL due to a changing angle of attack minus delta PU due to a changing angle of attack, x minus c over 4 times dx times b. And the delta in the pressure, according to thin airfoil theory, is actually exactly equal to the changing angle of attack times the flat plate solution. So that integral actually would be equal to 0 no matter what the airfoil shape is. Right? So that is because if you focus just the delta of the pressure instead of the pressure itself, then this is universal. So as an example, I'm using this really weird airfoil over here, right? So basically this is to show whatever the airfoil is, no matter how weird the pressure distribution is originally, so basically 2 degrees angle of attack is the pressure distribution in the middle. So at 2 degrees angle of attack, right, we have a suction just near a little bit up of the leading edge, and we have a stagnation point, right, Cp equal to 1, a little bit below the leading edge, and the pressure goes like this, and it goes, reflects, and then comes back, right? So that's the pressure distribution at 2 degrees angle of attack. Now, if you look at how the pressure distribution changes as you increase the angle of attack, of course, as you increase the angle of attack, the suction, right, at the leading edge increases, and basically there is a gap of delta PU. There is a corresponding gap. Let me see, where do we get? Yeah, there is a corresponding gap over here of delta PL. And the gap between 2 degrees and 4 degrees angle of attack is not a function of the shape of the airfoil, right? It only depends on, it is the flat plate solution. So as a result, the change in the moment around the quarter chord should be 0, right, for thin airfoils. And that can be seen over this X-foil calculation, right? So you can see the lift changes dramatically as you go from 0 degrees to 4 degrees. The moment coefficient, which in X-foil is actually the moment around the quarter chord, that stays pretty much the same, right? The difference in that moment is really due to the thin airfoil theory only being an approximation, right? For example, at the leading edge, you don't expect thin airfoil theory to hold because the assumptions is not really true, right? The thin airfoil theory always assumes the flow at the surface of the airfoil is primarily in the x direction. The y direction velocity is much, much smaller. That's not going to be true over here. It's not even really true over here, right? So there is a little bit change in the CM, but it is really, really small, especially compared to the change in CL. Yes, question?
You wrote earlier that the moment around the quarter chord would be 0 if the P lower is P flat plate and the P upper is negative P flat plate.
Yeah.
When you subtract PL minus P, wouldn't that just give you 2 P flat plate?
Yes, right. So if you have a flat plate thin airfoil theory solution, basically at a finite angle of attack, the upper surface would have a negative pressure, the lower surface would have a positive pressure, and the pressure is symmetric, right, on the upper versus lower surface. Yes?
So in the solution, that's the constant multiplied by the flat plate solution to give 0 moment.
Gives 0 moment around the quarter chord. Yes. Yes, that's the most important lesson we get from the thin airfoil theory, right? And up to the precision of the assumptions of thin airfoil theory, this is true. And basically the difference in the CM you can see here gives you really how accurate thin airfoil theory is. All right, does that make sense? Okay, and now armed with that knowledge, we can start to really think about how do we assess the stability of a wing or airfoil just from CL and CM alone at a single point. For example, let us focus on the 2-degree angle of attack. Let's focus on the 2 degrees angle of attack. And the question is given the definition of CL and CM, so let me just rewrite it down. CL is equal to the lift divided by half of rho u infinity squared times the chord times the span, right? So that's the lift coefficient. On the other hand, Cm, the moment coefficient, is equal to the moment around the quarter chord. All right, when you say the moment coefficient, by default, it is around the quarter chord of the wing. And if the wing is swept or whatever, it's the mean. It's the chord-weighted average of the quarter chord. Okay, so half of rho u infinity squared and C, B. Okay, so what is the unit of moment? In order to make Cm also non-dimensional, is this enough, or is there some extra scale we need to divide or multiply? Another distance, right? Moment is equal to force times distance. So we have to divide by another distance scale for this to be non-dimensional. And in this case, the thing that makes most sense is the chord itself. Okay, so this is how we define the moment coefficient. It's just dividing by exactly the same thing as we normalize the lift, except for there is another chord length inside it. All right. One way to think about it is that if you put the airfoil at a unit aerodynamic pressure, right, half of rho u squared is equal to 1, with a unit chord and the unit span, how much moment do you get? Similarly, CL is if you have a unit aerodynamic pressure, unit span, unit chord, how much lift do you get? Right, so that's an easy way to think about it. Okay, now if you think about it in that context, right, unit aerodynamic pressure, unit chord, unit span, I have a lift of 0.0786 and I have a moment of 0.055. Where is the center of lift? How do you calculate the center of lift from just these two numbers? Okay, maybe an easier question to start with is, okay. So I forgot to tell you the sign. Okay, by convention, the sign for Cm is actually like points into the board. So a positive Cm would be a nose up moment. A negative Cm would be a nose down moment. Right. So that's the convention for the sign of the moment coefficient. Similarly, lift, positive means pointing up, negative means pointing down. Moment, positive, nose up, negative, nose down. All right. Okay, so given these two numbers, is the center of lift upstream of the quarter chord or downstream of the quarter chord? Upstream. Why?
Because since the moment's positive, we know that the moment at the quarter chord would be 0, then it would have to be before the quarter chord.
Right. So think about what the center of lift is, right? The center of lift is a location at which the moment around that location is equal to 0. Right? So if at the quarter chord the moment makes you nose up, where would you have to be to make the moment around the point equal to 0? You have to be further upstream, right? So basically, what it is saying is that if the moment around the quarter chord, which is equal to the integration of pressure difference, PL minus PU, right? X minus a quarter chord dx times B. So if that Actually, let me make sure the sign is correct. So if PL minus PU times X minus that would be a nose down moment, right? That would be a nose down moment. So in order to make sure the moment has a sign that is consistent with the conventional definition of the moment coefficient, I think I have to make a negative sign on the whole thing. So I would need a negative sign on the whole thing in order for the moment to be a nose up moment, as opposed to a moment that points out of the board, a nose down moment, right? Okay, so if this is a positive number, then the question is where a moment, let's say a center of lift, MC, that around which the moment is 0, right? That has to be equal to the same integral minus PL minus PU times X minus that center, right? Let me just say XC because I don't want to confuse with the code dx. All right. So now if you make that calculation, if you split the integral into two parts by subtracting c over 4 and adding another c over 4 inside the parentheses, what you get is that you're going to see the same thing, but c minus c over 4 dx and another term, right? Plus b times integration of 0 to c, PL minus PU, now c over 4 minus xc dx. Right? Okay. So what is the first term? The first term is just the moment around the quarter chord. So first term is the moment around the quarter chord. Let me just call it XC so that we don't confuse with the chord. Okay, so that's the moment around the quarter chord. That's the first term. And what is the second term? The second term, c over 4 minus xc, is a constant in the integral, so we can pull it out. After we pull it out, it's simply an integral of the pressure on the upper surface minus the pressure on the lower surface times dx. What is that? What is the integral of the pressure difference? It's lift, right? It is just the lift. So let me pull this thing out. We get, well, because for lift you don't need the negative sign, so we'll reverse this. So xc minus c over 4 times the lift, right? So now what we can see that for a positive moment around the quarter chord and a positive lift, right? If the sum of them has to be 0 and both M and L is positive, xc minus c over 4 has to be negative, right? Which means xc has to be upstream of the quarter chord. Now from the same formula, you can infer other combinations. For example, if the moment coefficient is negative and the lift is positive, then xc is going to be downstream of the quarter chord. There are two other combinations corresponding to the lift being negative, right? So if lift is negative and moment is positive, then the center of lift, the center of the negative lift, is downstream. If both lift and moment are negative, right, the center of that negative lift is going to be upstream of the quarter chord. So that's the only 4 possible combinations. And then you can also calculate exactly where the center of lift is by just combine this equation a little bit. So xc minus c over 4 is going to be equal to negative of m c over 4 divided by L. So if you look at how the L and M are non-dimensionalized, this is just the Cm over Cl minus times C. That gives you exactly, right? So basically minus of Cm over Cl gives you in percentage chord how much the center of lift is different from the quarter chord. All right, make sense? This also is another way to figure out, okay, how does the center of lift shifts as you increase or decrease the angle of attack? Because according to thin airfoil theory, right, Cm does not change as you change the angle of attack, but Cl does. Cl does, right? So if Cl is positive, for example, so let's say if Cl is positive and Cm is also positive, as you change the angle of attack, as you increase the angle of attack, you get a bigger denominator, right? You get a bigger denominator. So Cm over Cl is going to be less positive as you increase the angle of attack, right? And Xc would then be, Xc minus C over 4 would be less negative as you increase the angle of attack. Less negative means Xc, although still ahead of the quarter chord, is going to shift towards the quarter chord, right? Okay, that's a stable situation because the center of lift shifts downstream as you increase angle of attack. So you can make different reasonings that way. All right. Okay, and to be more precise, if you don't want to rely on thin airfoil theory, you can actually plug in these numbers, Cm over Cl, Cm over Cl, Cm over Cl, to see how the center of lift shifts as you change angle of attack. Right, that's a more precise way, especially if the numbers, especially if the moment coefficient is actually pretty close to 0, then you should not really trust the thin airfoil theory, right? Because I mean, for here, the moment coefficient is about an order of magnitude larger than the error of the thin airfoil theory, so it's okay, right? But if the moment coefficient is 0.00 something, then that's a place where the thin airfoil theory is no longer that trustworthy, right? And it's better to actually calculate the numbers and make decisions according to the numbers. And also, the error of the thin airfoil theory is going to be larger if the airfoil is thicker, right? So that's again another scenario where it's better to get the Cm and Cl at different angles of attack and then make a decision about stability. Okay, questions so far? Right after, I'm going to ask you to do a very similar calculation, but for a different set of airfoils. Okay, I'm going to ask you to look at not just not multiple calculations, but a single calculation on an airfoil and determine if that airfoil is going to be stable or not. All right. So this is the exercise. I have just these two airfoils. I think I'm motivated all the stability analysis with NACA 0012 and the NACA 4412, right? And here the calculation is around the single angle of attack. And I would ask you to use the result of the thin airfoil theory, namely Cm does not change as you change the angle of attack. To estimate, okay, what is the center of lift for both airfoils at Cl equal to 0.4 and 0.5? Note that here we don't have the same Cl, right? Here Cl is 0, here Cl is 0.5 something, right? So I want you to use the result of thin airfoil theory to estimate where is the center of lift for these two airfoils? Oh, and I forgot to mention that for thin airfoil theory, the change in lift, the change in moment, right? Changing Cm is equal to 0 for thin airfoil theory, and changing Cl is equal to 2 pi a change in alpha. So that's also from the flat plate solution. All right, so how do you use this to estimate where the center of lift is? And the 2 is that suppose you are flying upside down, right? Then the lift coefficient would be negative. Can you estimate if you fly upside down, would these wings be stable or not? So please form groups of 2 or 3 and starting working on these two problems.
Use also you can use it for negotiation. Like
You're like as if I'm gonna negotiate with another company over around $26 an hour.
yeah,
literally.
Okay, so for some of you who are done with both questions, and I think for those who are done, I've seen the result being correct so far. There is a third question. So imagine I have these two airfoils, and the symmetric airfoil is placed 1 chord behind. So there is a gap exactly equal to 1 chord length. Okay, between this airfoil in the front and this airfoil at the back. Now, is the airplane stable?
Yeah, there'll be some stuff right now.
So because the two wings are the same size, right? You can either think about this as the horizontal stabilizer, this as the main wing, or you can think about this as the canard, this as the main wing. Either way is fine.
Probably would have.
Yeah. Okay, so maybe let me do the third question over here, because I see a lot of difficulties among all the groups. So I think makes a bit of sense for me to just go through the whole process. So first the question, I think everybody got it, right? So the NACA 0012 is neutrally stable, and the 4412 is unstable, right? Everybody got it? And for the second question, right, it doesn't make any difference for the symmetric airfoil to fly upside down or not. So it's still neutrally stable, and the 4412 now is stable. There is actually a lot of questions on why it makes sense for the center of lift at CL equal to minus 0.4 to be ahead of the leading edge, right? So I think everybody got the negative center of lift, right? So it makes sense because if you do a calculation, let me do it here. It takes a, okay, X-foil, NACA 4412, alpha minus 5 degrees. Let's see what you get. You get a very high peak of force downward near the leading edge, right? Remember, the flow comes at a negative angle downward. So you get a downward lift near the leading edge, but the pressure between upper and lower surfaces flips over at this location. So you get a positive lift over here, right? So let me just draw it over here. Draw it on the board. So imagine you have an airfoil placed upside down, and when you have this at the positive angle of attack, you basically get a lift over here, and then you have a smaller lift on the afterwards portion of the airfoil. So remember, what is the center of lift? It is the location around which the entirety of the distributed lift force has zero moment. Right? So where is that location? Well, it cannot be behind here because the moment of this force is going to be less than the moment of this force, right? If you put a point over here. So the total moment would not be 0. It can also not be here because then this force and this force has the same direction of moments, would not be 0. It has to be somewhere over here, right? For this bigger force with a smaller arm to cancel the moment of this smaller force but with a longer arm. So the center of lift for this kind of pressure distribution is going to be over here, right, before the leading edge. So that's perfectly reasonable center of lift. Right, make sense? Yes?
Is it generally true that an unstable airfoil, when you flip it, becomes stable?
Oh yeah, that's a very good question. Is it generally true? Think about if you think about thin airfoil theory, right? Okay, so without thin airfoil theory, I don't know the answer. It may or may not be true. But if the airfoil is thin enough and the angle of attack is small enough so that thin airfoil theory holds, then whether the airfoil is stable or not simply depends on the ratio of Cm and Cl being positive or not. Right? So if the ratio between Cm and Cl is negative, as in this case, the airfoil is unstable. But if the ratio between Cm and Cl is positive, just like you flip the airfoil upside down, then it is going to be stable. All right, so that would be yes, right? So similarly, if you have a stable airfoil, and you flip it, it would be unstable. If we trust the result of thin airfoil theory. All right. Okay. Yeah, good question. Good question. Now, a lot of difficulty lies on the third question. And to answer this question, we really need to go first principle, right? We still have to figure out, okay, where is the center of lift at CL 0.4? And where is the center of lift for CL 0.5? So the first thing to figure out is what is the definition of the center of lift? It's still where the force, where the location has to be for the total moment to be 0, right? So basically, let me say, if the center of lift is xc, then the moment around xc, which is equal to now the integration from 0 to 3c, right? If we treat 0 as the leading edge of the first airfoil, pu minus pl, I just integrated the negative sign into the sign of the pressures, x dx would have to be 0, right? Let me just say 1 over b, so that we don't have to carry the b in the entire thing. Okay, and that we can split into integration from 0 to c. Sorry, this is x minus xc minus xc. Okay, so we are going to split an integral from 0 to c, and we are going to split x minus xc into x minus xc1, the center of lift for the first airfoil, plus xc1 minus xc, the aerodynamic center of the whole system, dx, right? And then we are going to add the integration from 2c to 3c for the aft airfoil, pu minus pl. Again, we split the x minus xc into the same two parts, x minus xc2 plus xc2 minus xc. Why are we splitting it like that? We are splitting this term like that because if we look at only the first term, x minus xc, when we multiply with the pressure difference and integrate, we know the integral is going to be what? Remember, xc1 is the location of the center of lift of the front airfoil, right? So by definition, what is the integral if we only multiply the first term? 0, right? That's how we define the center of lift. All right, it's the moment is going to be 0. The second term is a constant that can be pulled out of the integral, right? So what we get out of the first integral is 0 plus this constant xc1 minus xc times, okay, now what is the integral of the pressure difference over dx? It's just the lift, actually the negative lift, right? So what we get is this times negative lift, well, also divided by b. Okay, that's the first term. The second term is the same. You get 0, right? And then xc2 minus xc times minus lift. So that's the lift of the first airfoil. That's the lift of the second airfoil divided by b. Okay, so what do we get? We get 0, which is the sum of the whole thing. Has to be equal to, if we normalize the L's, has to be equal to L1 times xc1 minus xc plus L2 times xc2 minus xc, right? Or, in another sense, xc is going to be the weighted average of these two axes. So xc1 times L1 plus xc2 times L2 divided by L1 plus L2, right? Right? So that's basically what we commonly get from mechanics, right? If we have two forces, one at one location, another at another location, the center of these two forces is the weighted average of the location of these two forces, and the weight is the respective force. Okay? By the way, this is also how you get a negative center of lift if you have a case like this, right? When you have, for example, L1 positive, L2 negative, then, well, you do the weighted average, you can get something like actually way off if one of these is of a different sign. Okay, so this tells us in order to get the center of lift of the entire system, we need to know not only the respective center of lift, but also the respective lift, right? Okay, so now let's figure out what the lift is of this airfoil and this airfoil if the average between these are 0.4 and 0.5. How do we figure that out? Any suggestions? How can we get from these numbers, right? If we know at 0 degrees angle of attack, the lift is 0 for this one, and the lift is 0.51 for this airfoil, how do we get, by the way, what is the average, the lift at 0 degrees angle of attack? Right, just a half of this number, right? Okay, so to get an average lift coefficient of 0.4, what do we need? We need to increase the angle of attack, right? Okay, as we increase the angle of attack, how does the lift of both airfoils change? Well, they'll increase linearly at the same rate, right? Delta CL is equal to 2 pi delta alpha for both airfoils, if we trust the thin airfoil theory. Okay, so in order to go from this CL, these pairs of CL, to an average CL of 0.4, right? We just figure out how much difference we need to, how much delta CL we want on average, and both airfoils are going to have exactly the same delta CL. Okay, so basically for this airfoil, right, so let's say if the mean, if CL bar is equal to 0.4, okay, that means delta CL is equal to delta CL bar, right? which is gonna be equal to 0.4 minus half of 0.51. 0.51 is the CL of the second airfoil. Agreed? Okay, so that means my CL for this airfoil has to be just that number. What is that number? It's a point. Sorry, 145. Thank you. And what is the CL for this airfoil? It should be 0.145 plus 0.51, right? Which is what? 655, right? Good. Okay, so now we have the respective CLs of these two airfoils. What are their respective center of lift? Well, again, we use the fact that the CM does not change, right? So basically, the XC for this airfoil is going to be a quarter chord, right? Let me just say XC over C is going to be a quarter chord plus 0.1112 divided by 0.655, right? So on this one, XC over C is always going to be a quarter, right? Okay, so now we just need to average these two center of lifts, right? For this one, XC, if we consider this airfoil is way behind, we have to add 2, right? In order to consider that this is actually way behind. So the center of lift is going to be, let me just file up my calculator, which is just a Python. All right, and that is going to be, so quarter plus 0.1112 divided by 0.655. That's the center of lift of the front airfoil. If I missed something, let me know. Times the CL 0.655 plus the center of lift of the after airfoil times its lift 0.145, and the whole thing has to be divided by the sum of the lift coefficients, which we know is 0.8, right? Any questions about that? So that's basically just this formula over here, right? Okay, so that we get is going to be 0.7515. So XC at CL equal to 0.4 is equal to 0.7515. Okay, so similarly, we can just calculate what is the corresponding lift at CL 0.5. For CL 0.5, the sum of the CLs is going to be 1, right? And the moment, let me see. For the front airfoil, the moment doesn't change, so this doesn't have to change, and the CL has to be increased by 0.1, so it's going to be 755. All right, and it's going to be 755, and for the after airfoil, the center of lift doesn't change, and the lift coefficient becomes 0.245, right? Okay, and the center of lift is going to be 0.8512. So the center of lift at CL equal to 0.5 is going to be 0.8512. All right. Is this a stable configuration or not? The first one is almost neutral. What do you mean by that?
Well, the quarter of 3 would be 0.75, right? Is that okay?
Okay, so you have mentioned the quarter chord of this entire thing, right? Considering the gap in between is 0.75. That is not the right way to think about it. This is because if you think about what the thin airfoil theory predicts, okay, taking the entire chord length of 3 and multiplied by 1/4, it's equivalent of saying if you increase the angle of attack of the whole thing, the flow changes in a way that is similar to a flat plate between this and this. Okay, that is not the case. A flat plate solution requires a bunch of vorticity distribution from here all the way to here, including in the gap. That's not realistic, right? Because in order to simulate the flow around the airfoils, we place source and sinks and vortices inside the airfoils. These are realistic flows. But if you place vortices in free space, it's not a valid flow solution. Because the vortices, as remember the vorticity equation, the vortices will be convected downstream. It's not going to be a steady state flow field. Instead, what you should get is, as you increase the angle of attack, you have a flat plate solution over here. You have a separate flat plate solution over here. Right? So the vorticity distribution, the additional vorticity distribution you get, has this shape over here and has another this shape over here. The average of this is going to be actually the average of a quarter chord of this one and the quarter chord of this one. It's actually going to be 1.25. All right? Does that make sense? Yeah, so that's actually a very good way to think about the average aerodynamic center, the average quarter chord. It's not a quarter from the leading edge of the first wing to the trailing edge of the last wing. It's not that case. It is taking each individual wing and look at what is the aerodynamic center of each individual wing, and then average them weighted by the area of the wings, right? Because that's how strong these flat plate solutions are. Okay.
So in this case, we just say
In this case, right, still the fundamental first principle of stability is where the forces shift as you increase or decrease angle of attack. So in this case, how does the force shift? Backwards, right? As you increase the angle of attack by therefore increasing the CL, the center of lift shifts backwards. And that's a nose down moment if the center of lift shifts backwards. Again, like for example, if the design CL at a certain speed is 0.4, right, then the center of lift has to coincide with the center of gravity, which is going to be 0.75-ish. If you pitch up, the center of gravity doesn't change, but the center of lift shifts to 0.85. That'll create a nose down moment. The gravity is no longer going to be balanced with lift. Gravity points down here, lift points. Gravity still points down here. Lift now points up here. So it's going to restore the whole airplane to a neutral location. All right. So so this is the end of the lecture. But this is really giving you a sense of how multiple wings impact the airplane stability. So if you have a horizontal, you have a wing and a horizontal tail. You put the horizontal tail at a lower lift coefficient than the main wing, right? Either by having a lower angle of attack or having a less camber, you're going to increase the stability of the whole airplane. So we'll see you next Monday and start in recitation Friday, and next Monday to start discussing three-dimensional potential flows.